Imagine installing a product that takes about 4 hours to apply in your attic, costs a few $100s in materials, and reduces your summer cooling bills by 20 to 35% for the entire time you own your home. That's the value proposition of radiant barrier attic insulation, a proven technology developed through NASA research during the 1970s that has produced documented savings across millions of installed applications in hot climates. The barriers work by reflecting radiant heat rather than resisting its conductive passage as conventional insulation does. In hot climates where attic temperatures regularly exceed 150 degrees Fahrenheit during summer days, this reflective barrier prevents massive radiant heat gains that conventional insulation only partially addresses. The result delivers dramatic cooling cost reductions while improving comfort in rooms directly below attics where conventional insulation alone leaves occupants sweltering despite air conditioning running continuously. Understanding how radiant barriers work, what proper installation involves, and where the technology fits contemporary energy efficiency strategies helps explain why southern U.S. states have progressively adopted radiant barrier requirements in building codes, while colder regions appropriately determine the technology matters less for their specific climate conditions. The physics of radiant barrier performance involves reflection of infrared radiation. That constitutes the primary heat transfer mechanism between hot roof decks and cooler ceiling insulation below. Summer roof decks heat to 150 to 180 degrees Fahrenheit in hot climates, radiating intense infrared energy downward into attic spaces. This radiant energy transfers through attic air largely unimpeded, heating ceiling insulation surfaces and eventually transferring heat into living spaces below. Radiant barriers with low emissivity surfaces reflect 95 to 97% of this incident radiation back toward the roof deck, dramatically reducing the radiant heat load that conventional ceiling insulation must manage. The approach doesn't replace conventional insulation, but rather complements it by addressing the radiant heat transfer that conventional insulation alone cannot effectively stop. The low emissivity surfaces that make radiant barriers work typically consist of thin aluminum foil applied to paper, plastic, or fabric backing materials. The aluminum surfaces must remain exposed to airspace rather than being covered by other materials, because direct contact with other surfaces transfers heat conductively rather than allowing the radiant reflection that provides the performance benefit. The required airspace of even 1-inch depth provides adequate function for most applications. The aluminum surface must remain reasonably clean across operational lifespans. Though dust accumulation moderates performance only gradually rather than eliminating it entirely. The historical development of radiant barrier technology emerged from NASA space program research during the 1970s, exploring thermal protection approaches for spacecraft and space stations. Researchers discovered that thin reflective surfaces could dramatically reduce radiant heat transfer in applications where traditional insulation approaches had been used inadequately. Translation of these findings into terrestrial building applications proceeded through the 1980s, with commercial products emerging in the early 1990s and achieving broader adoption through the 2000s and 2010s. The technology progression from space applications to mainstream building products demonstrates how space program research produces terrestrial benefits beyond its original aerospace applications. Dr. Consuela Rivera Hernandez, a Mexican-American building energy researcher who has studied radiant barrier performance in hot climates for over 2 decades, has documented how proper installation produces consistent energy savings across diverse home configurations, while improper installation can substantially reduce or eliminate expected benefits. Her research at institutions across the southern United States has contributed to installation guidelines and code requirements that support reliable performance. The Research Foundation provides evidence-based support for adoption while identifying the installation quality factors that determine whether individual installations achieve available benefits. The installation configurations for radiant barriers include several effective approaches that suit different building configurations. Direct roof deck application attaches radiant barrier material directly to the underside of roof sheathing, typically using a foil-backed plywood product or aftermarket spray-on radiant barrier paint. Attic truss application drapes radiant barrier material over attic trusses, creating an airspace below the roof deck. Floor of attic application places radiant barriers on top of existing ceiling insulation facing upward into the attic space. Each configuration provides benefits in appropriate applications with selection, depending on attic access, existing construction, and specific performance objectives. The new construction integration of radiant barriers has become routine in hot climate residential construction. Foil-backed roof sheathing products provide integrated radiant barrier function at modest cost premium, typically 20 to 40 cents per square foot additional compared to conventional sheathing. The integrated approach eliminates installation labor by incorporating radiant barrier function into already required sheathing materials. Building codes in Texas, Florida, and many southwestern states increasingly require or strongly incentivize radiant barrier installation in new construction, acknowledging the proven energy benefits and supporting utility demand-side management initiatives. Kweku Antwi Boadi, a Ghanaian-American building energy analyst working with utility energy efficiency programs across the American South, has documented how radiant barrier rebates and incentive programs produce favorable participation rates and measured energy savings. His program evaluations show that participating homes typically achieve 15 to 30% cooling energy reductions, matching laboratory predictions and supporting expansion of similar programs across additional hot climate regions. The utility program experience provides evidence that radiant barrier adoption can be substantially expanded through targeted incentive programs, addressing both material costs and installation labor investments. Now for the obstacles and limitations that affect radiant barrier applications. First, the climate applicability limits benefits to hot and mixed climates with substantial cooling seasons. Radiant barriers primarily benefit cooling performance while providing minimal heating season benefits. Cold climate installations produce negligible savings that don't justify the investment. The climate considerations appropriately restrict radiant barrier recommendations to specific climate zones rather than applying universally, regardless of local conditions. The climate-specific applicability distinguishes radiant barriers from more universally applicable efficiency measures. Second, the installation quality requirements affect whether installed products achieve expected performance. Radiant barriers require adequate airspace, proper orientation of reflective surface toward appropriate direction, and installation without gaps or short circuits that could undermine performance. Inexperienced installers can produce installations that look adequate but deliver reduced benefits. The quality sensitivity supports using experienced installers or detailed specifications that address critical installation factors explicitly. Third, the dust accumulation concerns reduce performance gradually over extended installations. Reflective surfaces accumulating dust see modest performance reductions as the low emissivity surface becomes partially coated. Most installations retain 80–90% of original performance after 10–20 years of operation, with additional gradual reductions continuing thereafter. The performance reduction is modest but should be understood when evaluating long-term benefits. Fourth, the product variability across manufacturers affects installed performance substantially. Products with higher quality aluminum coatings, better backing materials, and proper installation hardware perform substantially better than budget alternatives. The product quality considerations affect economic analysis that should compare total life cycle performance rather than just initial material costs. Premium products with 25-year warranties typically justify their cost premiums through superior long-term performance. Fifth, the interaction with other efficiency measures requires consideration. Homes with comprehensive attic insulation, properly sealed ducts located in conditioned spaces, and radiant reflective roofing materials may achieve limited incremental benefits from radiant barrier additions, since other measures have already addressed portions of the heat transfer they would address. The integration considerations support systematic efficiency approaches that coordinate multiple improvements rather than pursuing individual measures in isolation. Despite these considerations, radiant barrier technology represents proven cooling efficiency, improvement for hot climate homes that delivers substantial returns on modest investment. The comfort improvements in rooms directly below radiant barrier-treated attics exceed what measured cooling savings alone capture. Upstairs bedrooms in two-story homes and rooms directly below attics commonly experience notable discomfort in hot climates, despite air conditioning running continuously. Radiant barrier installation reduces ceiling surface temperatures substantially, eliminating the radiant discomfort that occupants experience when ceilings are hot, even if air temperatures are moderate. The comfort improvements particularly benefit sleep quality in upstairs bedrooms, where radiant heat from hot attics above can affect sleep comfort despite climate-controlled air conditions. The economic analysis of radiant barrier investment varies substantially based on climate severity, cooling electricity costs, and installation approach. Hot climate homes using electricity for air conditioning typically achieve 2 to 5 year payback on radiant barrier investments through cooling cost reductions alone, with continued benefits across 25 to 40 year effective lifespans. Cooler climates produce longer payback periods that may still justify installation for comfort benefits, even when pure economic returns aren't as compelling. The economic variability supports climate-specific analysis rather than universal recommendations. Teresa Arango Rodriguez, a Colombian mechanical engineer specializing in tropical residential cooling systems, has documented how radiant barriers perform exceptionally well in tropical climates where sustained hot weather produces consistent cooling loads throughout the year. Her measurements across Colombian coastal and lowland projects show cooling energy reductions of 25 to 40% from radiant barrier installation, consistently exceeding results from temperate hot climates due to the continuous high temperatures that tropical climates produce. The tropical performance validates radiant barriers for applications beyond the temperate hot climates where most performance documentation has occurred. The integration of radiant barriers with other roof system improvements produces compounded benefits beyond what individual improvements achieve. Reflective roof coatings, thick attic insulation, proper attic ventilation, and sealed HVAC ducting all complement radiant barrier benefits. Homes combining comprehensive roof system improvements can reduce cooling loads by 40 to 60% compared to conventional construction, producing dramatic operating cost reductions alongside substantial comfort improvements. The system thinking produces better outcomes than pursuing individual improvements separately, while typically at lower total costs than fragmented approaches. The aesthetic considerations for radiant barriers are generally minimal, since installations occur in attic spaces typically hidden from regular view. The foil appearance of attic visible installations doesn't affect home aesthetics from living spaces or exterior views. Some radiant barrier products designed for aesthetic applications use less reflective surfaces that would reduce performance but maintain more conventional appearances in visible applications like exposed ceiling structures. Most residential applications use standard foil products in attic spaces where aesthetics don't matter. Olaniyi Ogundipe Ademola, a Nigerian-American residential construction consultant working with affordable housing programs in the American South, has documented how radiant barrier inclusion in affordable housing specifications produces substantial long-term cost savings for residents while requiring minimal additional initial investment. His program work demonstrates that energy efficiency improvements benefit low-income households disproportionately by reducing ongoing operating costs that impact household budgets substantially. The affordable housing applications show how efficiency technology can serve equity goals alongside environmental and economic objectives. The code requirements for radiant barriers in hot climate jurisdictions have progressively strengthened as performance evidence has accumulated. Florida building codes include radiant barrier provisions in their energy efficiency sections. Texas has adopted similar provisions through amendments to international codes. California's Title 24 energy efficiency requirements include radiant barrier credits in their prescriptive compliance paths. The code evolution reflects institutional acknowledgement that radiant barriers represent cost-effective efficiency improvements worthy of formal recognition and requirement. The retrofit applications of radiant barriers to existing homes produce substantial benefits in appropriate hot climate applications. Attic retrofit installation typically costs $1 to $3 per square foot of attic area, depending on installation configuration and contractor. Typical 2,000 square foot home retrofits cost $1,500 to $4,000, producing $200 to $500 annual cooling savings for 3 or 10-year payback periods. The retrofit economics work particularly well when combined with other attic improvements, including additional insulation, air sealing, and HVAC system improvements that can be efficiently installed during the same project. The research continuing on radiant barrier technology focuses on performance optimization, product development, and integration with other building systems. Advanced low-emissivity coatings potentially improving performance beyond current products remain under development. Integrated roofing products incorporating radiant barrier function into primary roofing materials simplify installation. Monitoring programs track long-term performance, providing data for future specification refinement. The continued development supports ongoing improvements in available products and application guidance across coming decades. Mei-Ling Chen-Yu, a Taiwanese architect who has integrated radiant barriers into contemporary tropical residential design, has developed design approaches that optimize radiant barrier performance through coordinated attic ventilation, insulation placement, and HVAC system integration. Her projects demonstrate that radiant barrier benefits extend beyond simple foil installation to include broader building design considerations that affect overall performance. The design optimization produces superior outcomes compared to basic radiant barrier installation alone, though requires more sophisticated design attention than simple product specification. The specific attic ventilation considerations for radiant barrier installations affect both performance and durability. Adequate attic ventilation removes air heated by roof solar gain before it can transfer heat into living spaces below. The ventilation works with radiant barriers to reduce overall heat transfer, with both technologies addressing different portions of the problem to complementary effect. Inadequate attic ventilation can cause moisture accumulation that affects radiant barrier long-term performance while also reducing thermal benefits from the combined system. Contemporary best practices integrate radiant barrier installation with verified adequate attic ventilation to produce systems performing reliably across extended operational periods. Jamshed Kazemi Barami, an Iranian-American building systems engineer who has studied integrated roof and attic systems in hot climate homes, has documented how system-level design approaches produce substantially better results than component-level specifications. His research demonstrates that homes with coordinated radiant barrier, ventilation, insulation, and ductwork improvements show 40 to 55% cooling energy reductions compared to conventional construction, while homes with only radiant barriers added to otherwise conventional construction show 15 to 25% reductions. The system-level benefits supporting coordinated improvement strategies rather than isolated measure adoption. The ductwork location considerations interact meaningfully with radiant barrier benefits in ways that affect whole home cooling performance. Ductwork located in hot, unconditioned attics experiences substantial heat gains that radiant barriers partially address through reduced attic temperatures. Ductwork located in conditioned spaces avoids these losses entirely, producing superior performance regardless of radiant barrier presence. Contemporary best practice for hot climate high-performance homes locates ductwork in conditioned spaces while incorporating radiant barriers to improve remaining attic conditions. The combined approach produces optimal cooling performance compared to either measure applied alone in isolation. The DIY installation possibilities for radiant barriers make the technology particularly accessible for motivated homeowners. Material costs for typical 2,000 square foot attics run $300 to $800 depending on product selection. Installation requires only basic tools, including staple guns, utility knives, and extension ladders. Most homeowners can complete installations over 1 or 2 weekends with modest assistance from family members or friends. The accessibility compares favorably with professional installation that might cost $1,500 to $4,000 for equivalent work. The DIY approach substantially improves economic returns while providing opportunity for homeowners to inspect attic conditions and identify other improvement opportunities. Consuelo Benitez Castaneda, a Salvadoran-American energy educator working with utility customer programs in Texas, has developed training materials that enable confident DIY radiant barrier installation. Her program materials address common installation questions, safety considerations for attic work, and performance verification approaches that help homeowners achieve professional quality results. The educational investment has enabled participating utility customers to access radiant barrier benefits at minimal cost while building household capability for ongoing efficiency improvements. The educational approach demonstrates how utility programs can support efficiency adoption through knowledge transfer rather than just financial incentives. The building material alternatives that incorporate radiant barrier function include foil-faced roof sheathing products, radiant barrier house wraps, and specialized roofing underlayments. These integrated products eliminate separate radiant barrier installation by incorporating the function into materials that construction already requires. The integrated approaches typically cost modest premiums over conventional alternatives while providing automatic radiant barrier benefits without separate installation labor. Contemporary hot climate new construction increasingly uses such integrated products to achieve radiant barrier benefits efficiently. The commercial and institutional applications of radiant barriers extend the technology beyond residential contexts. Big box stores, warehouses, schools, office buildings, and commercial facilities benefit from similar radiant barrier installations adapted for larger scales and varying roof configurations. The commercial applications often produce even greater absolute energy savings through larger roof areas, while achieving shorter payback periods through commercial electricity pricing that typically exceeds residential rates. Large-scale installations in commercial facilities have demonstrated particularly compelling economic returns that have supported substantial adoption in sectors where economic analysis drives efficiency investment decisions more strictly than residential contexts sometimes require. Magdalena Ostrowska-Malinowska, a Polish commercial building energy consultant who has analyzed radiant barrier applications in Central European commercial buildings, has documented how applications in warehouse and light manufacturing facilities produce cooling energy savings of 30 to 45% in appropriate climate contexts. Her analysis shows that commercial applications often benefit from simpler installation approaches than residential contexts, since commercial buildings typically have accessible roof structures that simplify installation. The commercial experience demonstrates that radiant barrier benefits extend across building scales and types, rather than being limited to residential applications alone. The fire safety characteristics of contemporary radiant barrier products meet relevant building code requirements without creating concerns that affect adoption decisions. Products designed for building applications carry appropriate fire ratings verified through standard testing procedures. Installation configurations follow code requirements for fire stopping and maintaining required clearances around electrical fixtures and penetrations. The fire safety performance of proper installations matches or exceeds conventional attic insulation products without imposing unusual restrictions on building design or configuration. The proven safety record across millions of installed applications provides foundation for continued code acceptance and homeowner confidence. The specific measurement methodologies for documenting radiant barrier performance have matured across decades of research to provide reliable techniques for individual project verification when desired. Infrared thermography documents ceiling surface temperature reductions produced by radiant barriers. Attic air temperature monitoring confirms the airspace temperature benefits. HVAC system, runtime monitoring documents, cooling load reductions during operation. Utility bill analysis tracks long-term energy consumption changes. The measurement toolkit enables verification of individual installation performance for projects where performance documentation supports incentive programs, efficiency certifications, or informed decision-making. The verification capability distinguishes radiant barrier applications from some efficiency measures where performance is difficult to document after installation. Consider what radiant barrier technology means for homeowners and builders in hot climates interested in cooling cost reduction and comfort improvement. The substantial cooling energy savings of 20 to 35% produce meaningful ongoing operating cost reductions across extended lifespans. The modest installation costs of several $100s for DIY applications to several thousand for contractor installations deliver favorable economic returns in appropriate climates. The comfort improvements, particularly in upstairs bedrooms, address common quality of life concerns. The new construction integration at minimal cost premium makes the technology almost universally appropriate in hot climate new homes. The retrofit applications deliver good returns for existing homes in applicable climates. The utility rebate availability improves economics further in many markets. The code requirements in progressive jurisdictions acknowledge the fundamental value of the technology. The question isn't whether radiant barriers deserve consideration in hot climate applications. The question is why adoption hasn't progressed further, given clear performance, economic, and comfort benefits in appropriate climate conditions. The answers involve awareness gaps and installation quality concerns, rather than fundamental limitations of the approach. For any hot climate home where cooling costs and summer comfort matter, radiant barrier technology offers proven solution delivering substantial returns on modest investment across decades of operation.